So hello everyone, my name is Marton, and today I will be presenting our work on improving the performance of today's big out-of-order CPUs by finding work that can potentially be done in parallel. But let's start from first principles. So we start with a program, maybe something like this, written in C++, and we go to a compiler. The compiler turns it into a graph consisting of basic blocks, which are just straight line code, connected by edges representing control flow. Then we can view the execution of this program as a walk of this graph. And out-of-order CPUs perform this walk by predicting the trace of visited blocks ahead of time, and then rolling an out-of-order window over it. So anything before the window is committed, and anything in the window is in flight, so we just check its progress, and we can do things out of order as long as we can find independent work. But how can we make the performance better? So we can't just increase frequency anymore because of power and heat. So we have to find other ways. So obviously one recent trend is going wider. So we enable multiple instructions to go in each cycle. This is conditional on us finding independent instructions to fill the pipeline width. Otherwise, it will sit idle and underutilized. And there can be some problems with this. So firstly, as the CPU is getting faster, memory operations remain slow, and therefore we get some relatively long latency operations. And these can, in particular, present a problem if they are involved in a dependence chain. So any instructions that are dependent on this load can't go before the load, and therefore we have to wait for that load. We start to run out of independent work inside the window, and we encounter underutilization, eventually stall. So clearly we need more independent work to fill those big structures. So we can look deeper into the trace. We can predict further ahead and have a bigger window. But with more prediction comes more chances to mispredict. It's worth noting that today's branch predictors are exceptionally good, but there are some branches that are just inherently hard to predict. So maybe we need to find independent work somewhere else. Parallelism could be a way to help us. So for example, task-level parallelism, here we are looking at iterations of a loop, and we transform the iterations into a sequence of updates that are sequential and bodies that are parallel. So this could lead to parallelization as shown here, where the body is overlapped with all future iterations. Well, this would be great, but it requires us to know that things are independent. And somebody needs to ensure that. Well, that can either be a developer, or it can be a compiler. So if it's a developer, then this process is unfortunately error-prone and time-consuming, and therefore expensive. If it's a compiler, well, the compiler is really good at being correct, but it's not very good at understanding the algorithm of the program, and it doesn't quite have the mandate to change exact semantics of the program. So in summary, we would like the compiler to do this, but we maybe need to help the compiler to do this. So what if we allow it to be wrong? What if the compiler just has to say, well, look, I found some work. It's probably parallel, but maybe not. Well, let's take a checkpoint at the start of each iteration. And this is just a snapshot of the architectural register state and the program counter. And this can help us fix any problems. So if the compiler is wrong, let's say iteration 3 and 4 have a conflict, then we can just cancel any speculative work that read stale input data. And fortunately, we have this checkpoint, so we can just reload it and rerun the iteration. But now we're executing instructions quite far ahead that are speculative. So where does all of this speculative state live? Well, if you allow speculative writes to write to memory, then we have a problem, because other cores could observe speculative state. And this is obviously a big no-go for today's architectures due to memory models. So maybe we should just constrain the state to inside the CPU core. We already have speculative state here, so why not add more? To constrain it, we can add a structure called the speculative buffer, and this will do a couple of things. So firstly, it will hold all the speculative state. It will serve the most up-to-date value to speculative contexts, and it will facilitate writing back to the memory system when speculative work is final. So how does this help us to get parallelism and speed up? Well, let's partition the resources inside a core, for example, the out-of-order window. So as before, we have committed instructions, and we have in-flight instructions. But this is just now one slice of multiple. And we call this the architectural thread. We also have a starting point. This can be the start of the next iteration. And this is where we start speculative work from. So let's have a second slice of the instruction window that can go through these. And let's call this speculative threadlet. I say threadlet because it's not OS visible, so it's purely microarchitectural. So as before, we have committed instructions between the starting point of the threadlet and the top of the window. And we have in-flight instructions inside the window. All of these instructions from the start of speculation can get canceled if the threadlet is getting canceled. And in-flight instructions can get squashed on a branch mispredict. So this would give us some speed up, but we also need to find where to speculate and when to start speculation. So let's use some help. The problem is that the microarchitecture doesn't have an overarching view of the program, but the compiler does. So let's use the compiler here. Let's put all of the sequential updates to registers around the edges of the loop, so up top into the header and on the bottom into the continuation. And let's annotate the boundaries of these regions with some hints. These could be ignored on like low-performance microarchitectures, or they can be used to spawn speculation. The top hint, detach, identifies where to start speculation at the bottom of the body. So this can lead to parallelism as before. The only difference is now, instead of a single update, we have a continuation followed by a header. So if we do this, we can get some speedups. It's worth noting that we haven't like doubled the size of the core or anything like that. We're just using existing resources and getting speedups from underutilization. The only new structure is the speculative buffer and some logic. So these are loops from the spec CPU 2006 suite. And as you can see, we're getting some good speedups on certain loops. But they don't cover the whole benchmark suite. So on the whole benchmark suite, we also get some gains, 9.4% geometric mean. We found that one class of loops that underperform are those with very small iterations. And our overheads for launching threadlets are very low, but at the range of like tens of instructions, they're not nothing. So let's try to amortize that cost by packing multiple iterations into each threadlet. The problem now, as you might have noticed, is we have this update in the middle. So we can just use value prediction on the registers. And we used very simple stride prediction and managed to get 2.2% extra speedup. This speedup comes from increasing performance on existing loops and also from covering some new loops. Well, thank you for listening to my talk. And this was a co-design effort, so I was involved in the microarchitecture and some of the architecture. And the rest of my group, well, Tim's group, but the rest of the group that I'm in, did the compiler and program analysis parts. I'd also like to thank ARM and EPSRC for supporting our research.